Hello, in this video, first one of Chapter 7, we will be talking about alkynes, specifically bonding in alkynes, and then in later videos we'll talk about properties and reactions of alkynes. But in terms of bonding, please read section 7.1. It's the introductory section to Chapter 7, and just those pages 256 through 257. Alkynes contain the triple bond, and I've drawn the picture of a particular alkyne. This is called propyne. It's 3 carbons with a triple bond. This is the Lewis dot structure. A little odd to call it that since there are no dots here, but that's always true when you have only carbons and hydrogens. So let's take a look at a ball and stick model for this molecule. Notice that in this particular kind of model kit that we're using, a triple bond is represented by 3 springs, all between the same 2 carbon atoms, so a triple bond. And then, of course, this is the hydrogen on the carbon right here, and this is the methyl group, the 3 hydrogens on its carbon. And notice the shape is, as we predict, straight across, so linear on this carbon and linear on this carbon. Notice that rotation around that central bond doesn't occur, but it really doesn't matter because rotating around it would not change the molecule at all. Rotation around this bond occurs just fine, and rotation around this bond, if it were to make a difference, also happens just fine. I'm going to go to the PubChem link so we can take a look at the 3-dimensional structure here. Okay, here it is, and notice straight line. So this carbon is 180 degrees straight across, this carbon is 180 degrees straight across. This carbon, of course, is tetrahedral, so it's 109.5 degree angles, but the important one in this case is the triple bond, and it is, of course, linear in shape, both carbons, and therefore the whole range of atoms from that one to that one to that one to that one, all in a straight line. And according to the Vesper model that we learned in general chemistry, since this carbon has 2 groups of electrons around it, it should be linear, 180 degrees, and since this carbon has 2 groups of electrons around it, again a single bond and a triple bond, just like that carbon, 2 groups of electrons, therefore linear, 180 degrees. This carbon, of course, would be tetrahedral, 109.5 degrees. That's what I refer to as model number 1. In other words, just looking at Lewis dot structures and Vesper model to figure out shapes of molecules. Now let's look a little bit more closely at the orbital picture here. This would be model number 2. So we have to assign hybridizations. So that carbon being linear is sp, 180 degrees. This carbon being linear, 180 degrees, is also sp. This carbon, we've learned if it's tetrahedral, it should be sp3 hybridized. So let's take a little bit closer look. And remember that this is what an sp hybridized orbital looks like. It's a combination of an s and a p, so it's called an sp. And this carbon, being sp hybridized, has 2 of these. So there we go. This is an sp orbital, and this is an sp orbital. There's a little tail on this one that's kind of hidden within the bigger part of the other one. Same thing here. And then, besides the 2 sp orbitals, there are also 2 more orbitals for a total of 4. And don't forget, every atom in that carbon, nitrogen, oxygen, fluorine row of the periodic table always has 4 orbitals. In this case, there are 2 sp orbitals and 2 p orbitals. So this is a p orbital up and down, and then another p orbital straight in and out. It's a little hard to represent that on a 2-dimensional surface, but that's what this is supposed to represent, a p orbital in and out. So all of these angles are 90 degrees. So here's another sp hybridized atom. So this one represents that carbon. This one represents that carbon. Since they're both sp hybridized, they look exactly the same as each other. Then what we're going to do is bring them together to overlap, because these carbons are bonded to each other. They must be overlapping orbitals. And so they overlap the sp orbital on this carbon atom and the sp orbital on this carbon atom, and that's going to form a sigma bond or a sigma overlap. This p orbital is still there, and it's, notice, up and down, perpendicular, parallel to this p orbital. And this one is parallel to this one on the other carbon atom. And notice then that besides the overlapping sp orbitals to form a sigma bond, these 2 parallel p orbitals overlap, and I've drawn just dark lines to represent the fact that this p orbital is overlapping with that p orbital. Really doesn't look like it because they're too far away, but if we could bring those in closer, you would see that they're actually overlapping with each other. And then this p orbital, in and out, is overlapping with this p orbital, in and out. So they're like this to each other. Again, overlapping both in front and in back. So this represents 1 bond. That's a pi bond, even though it's overlapping both on top and on bottom. It's not 2 bonds, that's 1. And same thing here, this is another pi bond. So there's a total of 3 sets of overlapping orbitals, this sigma overlap for what we call a sigma bond, this pi overlap, parallel pointing up and down, that's a pi bond, and then these two, in and out, parallel to each other, are also overlapping, so that's the second pi bond for a total of 3 bonds, and that's why we draw that as a triple bond. Now we also, of course, have this CH3 in this particular molecule, so all alkynes will have this array of orbitals overlapping in the middle to form a sigma and 2 pi's, one up and down and one in and out. But in this particular case, we also have a methyl group on it, so that's a tetrahedral carbon. I've drawn a tetrahedral, sp3, 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 4 orbitals, and they're going to overlap as well. There they go. And then, of course, all we have to do is worry about the fact that there's also hydrogen on here and 3 hydrogens on this carbon atom. So there they are. I've drawn s orbitals to represent the overlap with the s orbitals overlapping with the sp3 in this case and with the sp in this case. And then I went ahead and threw an electron, so 2 electrons there, 1 from the hydrogen and 1 from the carbon, 2 electrons here, 1 from the hydrogen, 1 from the carbon, 2 electrons here, 1 from the hydrogen, 1 from the carbon, 2 electrons here, 1 from this carbon, 1 from this carbon, 2 electrons here. By the way, that's just a shadow, so don't worry about that. But 2 electrons here, 1 from this carbon, 1 from this carbon, 2 electrons here, 1 from this carbon, 1 from this hydrogen, 2 electrons here in this overlap, 1 from this carbon and 1 from this carbon in that set of p orbitals overlapping, and then 1 in this carbon p orbital, 1 in this carbon p orbital, and again that's overlapping to form a 2 electron pi bond as well. So notice that this kind of sigma bond has free rotation because there are no overlapping pi orbitals, no overlapping p orbitals, no pi bonds there. That's just a single sigma bond, and we know that they can rotate freely. This bond right here is probably not rotating, but the fact is it really doesn't matter. As I've said here, it's irrelevant due to the linear geometry, whether it's rotating or not. We don't know, we don't care, it really doesn't matter. But do notice that there's no cis trans here because this is a 180-degree angle and this is a 180-degree angle. Straight across, no cis or trans. It's just 180 degrees straight across. And that concludes the lecture for today. Thank you.